Welcome back. This is video lecture 2.3, and today we're going to focus on the type of motion called free fall. Here's an example of what we mean. Piece of chalk. That's all that is, a piece of chalk. And I'm holding it up. Right now I'm holding it at rest, but we all know what will happen if I let go. There is an influence that we call gravity that causes its velocity to change. It accelerates. And we want to study that accelerated motion. Now, an alternative is I could throw it up, straight up, and let it come back down. Okay? That's the kind of motion we're talking about. It's called free fall, but we have to be very specific about what the conditions are we're assuming. But that's the simple idea. Motion along a line, in this case vertically, up or down, like so. We're not worrying about any sideways motion here, just up or down only. And the only influence that's causing the acceleration is what we call gravity. Okay, with that in mind, here is our first slide. The reading, if you want more detail and many example problems, is Chapter 2, Section 6. Okay. Free fall acceleration. Okay, so let's get the key ideas for free fall motion. First of all, what are the assumptions? What are the underlying conditions that make up free fall motion? That's what I mean by free fall motion defined. We mean any motion of a particle under the influence of gravity alone. That means, for example, if I'm taking this piece of chalk and holding it here, while I'm holding it at rest, it's not in free fall. Or while it's sitting on the tabletop, it's not in free fall. Or if I'm about to throw it straight upward, while it's in my hand and my hand is pushing it up, that's not free fall. And once it comes back down and hits on the ground, that's not free fall anymore. It's only free fall when the only influence on it is gravity. Okay? That means, for example, that we are going to be ignoring what is called air resistance, which you all have heard of. And for some things, like a piece of chalk going up and down, that's a reasonable thing to do, ignore air resistance. For other things, like a feather, that's not so reasonable, as you would know. However, if you want to watch an interesting video on the Wiley Plus site for this section, you can see a video where they took a cylindrical volume and using a mechanical pump, pumped out most of the air, a great majority of it, and then let a penny and a feather both fall in the evacuated cylinder, and they both hit the bottom at the same time. Okay? So if you can remove the effects of air resistance, even a feather would be included in what we're talking about. We're going to ignore the effects of Earth's rotation. That's a pretty safe thing to do unless the object is falling over a very great height. So that means that the distance over which the particle moves must be small compared to Earth's radius. So we're not talking about dropping something from the top of Mount Everest, for example. But for typical problems like we're going to be studying, like somebody drops a rock off a bridge and let it fall into a river, or takes a baseball and just throws it straight up and let it go up and come back down. Things like that, we're good. Okay? Those are distances small compared to the Earth's radius. If you're curious, by the way, as to what Earth's radius is in the SI system, it's 6.37 times 10 to the 6 meters. That's 6,370,000 meters. Okay, now here are some experimental facts for an object in free fall that have been validated many times by many different experiments, and we need to know all of these. First one, all objects in free fall near a planet's surface have the same constant acceleration independent of the object's mass. Note, constant acceleration. Okay? As long as it's in free fall, its acceleration is not changing. Guess what that means? We get to use those constant acceleration equations we introduced in the previous video lecture. And here's another thing that's rather interesting and somewhat surprising, that the acceleration, the constant acceleration that objects have in free fall, doesn't depend on the mass of the object. Here's that piece of chalk again. What if I replace this with an object same size and shape, but maybe it's made out of lead, the element lead, which you may know is very dense. And so if this were a piece of lead, same size as the piece of chalk, it would have a lot more mass than the piece of chalk. And yet if I were to drop this piece of lead, if this were a piece of lead and I dropped it and let it go into free fall, it would fall with the same constant acceleration as this piece of chalk. Galileo Galilei was one of the first to show this in experiments. What do we know about this constant acceleration for objects in free fall? That's the same for all objects independent of their mass. The direction of the free fall acceleration, vertically down in the direction of what we call a plumb line. If you're wondering what a plumb line is, there's a plumb line. I'll go back to the larger video so you can see it. It's just a piece of string with a heavy object on one end, and you just hold it and let it hang. And that gives you the vertically downward direction for wherever you are. Okay? All right, so the direction of this free fall acceleration is vertically downward. If you like, you could say towards Earth's center, or whatever planet you're on. And what is the magnitude of this constant acceleration? We're going to use a special symbol to denote just the magnitude of this free fall acceleration. The symbol is little g. Little g represents just the magnitude of the free fall acceleration. And we're going to take a pretty standard value for little g, assuming we are on Earth at what is called sea level. And that value for little g is 9.80 meters per second squared. Now it does vary around the surface of the Earth, and it varies with altitude. But we will take, for problems that we do, unless a problem specifically says otherwise, the magnitude of the free fall acceleration, the little g value, to be 9.80 meters per second squared. Of course, we could change the units. We could change the units of little g to centimeters per second squared. You get 980 centimeters per second squared. Or if we absolutely require the English system, where the unit of length is the foot, it converts to 32.0 feet per second squared. Let me please emphasize for you that the symbol little g is reserved in physics for the magnitude of the free fall acceleration of a particle. The magnitude of a vector quantity, acceleration is a vector with a magnitude and a direction. When you talk about the magnitude part of a vector, it's the size of it. It can never be a negative quantity. So little g can never have a negative value. And that is something that is very hard for people to absorb. A lot of times people end up writing this. G equals negative 9.8 meters per second squared. If you find yourself doing that, I can only emphasize very strongly, please stop. Little g can never have a negative value because it's, by definition, it represents the magnitude of free fall acceleration. And the magnitude of a vector can never be negative, period, full stop. So watch out for that. That's a sign that something's not right. If you have to end up substituting g equals negative 9.8 to have your work make sense, then there's been a mistake somewhere earlier in your algebra. Now, it's kind of interesting to look at a couple of real-world examples of what we would call free fall motion. I'm going to show you two videos from YouTube of free fall motion. The first is from the NASA Glenn Research Center here in Ohio, up near Cleveland, named after former astronaut and senator from Ohio, John Glenn. And at the NASA Glenn Research Center, they have what I'll call a drop tower, where they have a box in which you can put small objects that you want to study, and you let them drop over some number of meters, some tens of meters, and you can video record the motion while in free fall. So let me now convert to that video, and here you see, before I run the video, a box where you have your object to be studied and a video camera off to the side. And when I run the video, you see they're gonna put some bubbles in the box, close it up, and let it free fall. Putting in the bubbles. There's a camera over there to the left, closing it up. Okay. All right, so there we had a lab setup where you could study objects in free fall, in this case, soap bubbles. Here's another one at an amusement park. Person is about to be dropped into a net, okay? We're going to ignore the title of the video down here, right? And we're just going to run this.
I'm not scared and people think it is. I'll have to come back and do it. I get a plan to that chicken out on that ride.
Some people find this fun. Okay, so now, when was the free fall? You might want to think about that a minute. When was the particle in free fall? Well, the person was hanging there, still held up by the various ropes and so forth? No, because there are more influences than gravity. When the person comes in contact with the catching net? No, because there are more influences than gravity. Only when the person is actually falling, because then the only influence is gravity, assuming it's reasonable to ignore air resistance, which we will be doing in this chapter. Okay, so free fall is what we're studying. Now, here's a tip. Because a particle in free fall has constant acceleration, we get to use the constant acceleration equations to study the motion of a particle in free fall. Usually, you don't have to, but usually the vertical axis is denoted by a y instead of an x. Okay? So when a particle is falling or going up and then coming back down in vertical motion in free fall, the axis we tend to use for that is a y-axis. Okay? Okay, so in class we're going to do an example problem. That would be a Wiley plus type problem. That's a free fall problem. Here I want to just get warmed up by looking at a scenario that I'm sharing with you now on the screen. It is a baseball player standing on the ground holding a baseball who, at a certain time, throws the baseball vertically upward, okay, with an initial velocity straight up. The baseball travels vertically up, slowing as it goes because the acceleration is downward. Stops for 1 instant in time at its highest point. That's where it's shown right here. And then speeds up, falling vertically downward. Okay? Note that the problem specifies a plus y axis pointing vertically up with y equals 0 chosen not on the ground, but where the player releases the ball. Okay, that's a pretty basic physical scenario. We want to study this a little bit. And here's the first thing I want us to do. Part A. Make a sketch of the ball's velocity versus time. That is to say, I'm going to want you to make a sketch, a graph, where the velocity is plotted on the vertical axis and time is plotted on the horizontal axis. What would the velocity versus time plot for the baseball be? Take t equals 0 to be the moment when the ball is released. So what I'd like you to do is, in a moment here, pause the video, get yourself a piece of scrap paper, and try for yourself the sketch and see what you get, and then when you're ready, unpause it and come back and we'll discuss. Okay, welcome back. Did you make the sketch for yourself of velocity versus time for the baseball? Let's have a look of what it will be. There it is. Okay? Notice it is a straight line with a non-zero vertical intercept and a negative slope. Where did that come from? Well, there's a couple of ways to think about it. Here, I have constant acceleration equation number 1 from the last video. V final equals V initial plus AT, or just V equals V initial plus AT. And all I have to do is substitute in for the A negative G. Now let's talk about that for a minute. Okay? There's the acceleration value, or symbolic expression, I should say. Where did that come from? Well, the G is the magnitude part. The negative sign is the direction. Because remember, free fall acceleration is vertically down. But this problem chose the plus y direction vertically up. So the acceleration is in the negative y direction. That negative sign is therefore important. You must write it when you write down the expression for A. Okay? So again, the negative sign represents the direction of the acceleration, and the symbol G represents the magnitude of the acceleration. I hope that's clear. So in the constant acceleration equation number 1, for the A, I substituted the expression negative G. And that's how I get this result right here. And if I have that in front of me, I know that if I plot velocity versus time, this is the form of a straight line. Okay? It has the generic form y equals b plus mx, where b is vertical intercept and m stands for slope. And here the vertical intercept is the initial velocity, which is a positive value because the initial velocity is directed upward, right? There's the arrow representing the initial velocity. Okay? So the vertical intercept b is v0. Positive number. The slope is constant and it's negative g, it's negative slope. So that's why it's a straight line with a positive vertical intercept and a negative slope. And that means there's one instant in time right there where the velocity equals 0. That corresponds to when the ball's at its highest point. Okay? The other reason we know it's a straight line is because in a plot of velocity versus time, remember the slope of the tangent line represents the acceleration. But we know the acceleration is constant in free fall, so we need a graph that has a constant slope. That's of course a straight line. A constant negative slope. So a straight line with a negative slope. Okay? All right, now that's really good physics practice. And it's okay if you didn't get that graph right, but you want to pause this video and think about what I've been saying so that it's clear to you why that's the right graph for velocity versus time. Okay? Let's go back to the next question. B. What is the acceleration of the ball at its highest point? Up here, at that moment. What's the acceleration? I want you to think about that. Pause the video, think about it, get an answer, and then come back. Okay, welcome back. So, what is the acceleration of the baseball up there at the highest point? Did you say A equals negative g? Right? The acceleration is constant in free fall. And that means for every moment, from when it's released from the player's hand until caught again by the player, while it's in free fall, the acceleration is constant at the value negative g. Please note then, the acceleration is not equal to 0, even at the highest point. Acceleration is constant at negative g. What kinematic quantity is equal to 0 at the highest point? Do you know the answer? The velocity is equal to 0 at the highest point. For just one instant in time, the velocity is equal to 0. Because for that one instant in time when the baseball's at the highest point, it is momentarily at rest. Okay, that's another good physics question. At the high point of the motion, the velocity is 0, but the acceleration is not. All right, here's part C. Sketch the ball's acceleration versus time. I'd like you to do that for yourself, please. Sketch it on a piece of paper, pause the video so you can think about it, sketch it on the paper, and then come back. Okay, welcome back. Let's show our own sketch of the ball's acceleration versus time. So now what we're talking about is a graph where the acceleration is the vertical axis and time is the horizontal. What does that look like for the baseball? Did you draw that? What do we see here? We see a pretty simple looking plot. There's the time axis, so a value of 0 of acceleration is right there where the time axis is. Going up this way would be positive values of a, but our a, of course, is negative g. Okay? Negative, and then g is 9.8 meters per second squared if we're doing SI. So, our acceleration graph has got to be constant. It's got to be a horizontal line, and it's got to be at the value negative 9.8. And so it's just got to be a horizontal line going straight across on the negative side of A. And it's constant, right? So that's why it's horizontal. All right, one more. D. Sketch the ball's, y coordinate versus time. Again, pause the video, try it for yourself on a piece of paper, and then come back. Okay, welcome back. Did you draw? Well, first let me emphasize what we're talking about. We're talking about a plot where the vertical axis is y and the horizontal axis is t. What does that look like for the baseball? Note the baseball starts at y equals 0. So, did your graph look like this, is the question. Where did this come from? Well, let's start with constant acceleration equation number 2, but with y for the coordinate. Y equals y initial plus v initial t plus 1/2 at squared. Constant acceleration equation number 2 from the previous video. And now apply that to our scenario that we see in the picture here. For example, we know in this particular case that the initial y coordinate of the baseball is 0, right? Because we chose the origin to be where it's released. The initial velocity of the baseball is not 0. And for the acceleration, we're going to put in the symbols negative g. Sorry, that's behind the video, isn't it? So I'll write it again down here. And if you do that, you get this expression down here. Y equals v initial t minus 1/2 gt squared. That's what is used to make this graph. And notice it's quadratic in t. In fact, it is a parabola that opens downward at t equals 0, y equals 0, and at some later time, which if we had enough information we could calculate, it gets back to the release point. Okay? So it's a downward opening parabola. This is y versus t. Note then that the slope of the tangent line on this graph represents the velocity. So imagine following, say, with the palm of your hand, this curve, and let your hand follow the slope of the curve so that it always stays tangent. So when we start out, your hand slopes upward. That's a positive velocity. And as we go near the top of this parabola, our hand has to level off. So the slope is getting less, so the velocity is getting less. And when we're at the high point of this parabola, our hand is horizontal. Zero slope, so the velocity is 0. Beyond that, we're now going downward on the parabola, so our hand has a negative slope, so the velocity is negative. Okay? So that has to be the correct shape for the y-coordinate as a function of time. Okay, so that's our practice with free fall and our discussion of it. And like I said, in class session, we'll do more practice. But notice, it's an application of the constant acceleration equations to what is a pretty important scenario on daily life. And that's one of the reasons we talk about the constant acceleration equations to begin with, because free fall is one of those situations. Okay, that is all for this video.